All right, welcome. This is chapter 7. I think I'm going to end up doing 2 videos for chapter 27, but 27 is on color. So I will start with 27.1. And 27.1 is color in our world. So there is always that question, do you see the same colors that I see? Do we interpret them the same? And the answer is probably largely yes, but each person might interpret color differently. But color is not something that's actually real in the world, so to speak. But it's something that our brains interpret. So we would start, I think, by kind of dissecting what color is. We have essentially in a rainbow, and I think I've got right there. So a rainbow is the reds over here, orange, yellow, then they go green, blue, indigo, violet. So a lot of people remember the rainbow, Roy G. Biv. Some people argue that violet is not real, or indigo is not real, or whatever the case may be. I don't know. If it didn't come in a 8-pack of crayons when I was a 10-year-old, I don't know if it's a color or not. But the basic colors right there: red, orange, yellow, green, blue, indigo, violet. That's it. That's the colors. Everything else is not really a color. So we might have, I don't know if I have, I don't have brown. I can't make brown color. Hey, there we go. There's brown. So what you see here is brown. We recognize it as brown, but it's not a true color, meaning that there's no light that comes out in this color. This doesn't conform to a particular type of light, and we'll talk about why that is. But brown is just a combination of different colors, and so it's a mixture of colors that turn it into something else, and our brain perceives it then as brown. So let's start with, I forgot how to move this. It's been forever since I've done this. There we go. Let's start with in 27.2, which is selective reflection. So light sources like light bulbs, we got one hanging over me, the computer screen that you're looking at right now, things that emit light. Those things produce light and shine it off. But other objects just reflect light, like all of the stuff behind me, the bookshelf, the wall, the whatever else. That's all just hitting light. Light is hitting it, and it's bouncing off. So for most objects that is non-emitters, they just reflect light. Sorry about the handwriting here. I haven't used this pen forever, so I'm getting used to how high I have to pick it up for it to not drag. But this, I don't know what color that is up here, tanny looking thing, has light hit it, and some of the light bounces off of it, some of it doesn't. My other wall here is an accent wall. It's red. Light hits it. It's the same light coming from my light up here. It slams into both walls and bounces off. But in my tan, I don't know what color that is, wall, some light bounces off that makes it look tan. And on the red wall, the red light gets bounced off, and so that makes it look like it's red. So this is selective reflection or partial reflection. My shirt has two different types right here. It looks maroon, so it's reflecting lights, sources, bright light colors that look maroon, and so it doesn't absorb those colors, but it absorbs everything else that's not this color. The red wall absorbs everything that's not the red. The freaking whatever that is color absorbs everything that's not that freaking color. But then over here I've got gray on my shirt as well. So this gray absorbs most of the light that comes into contact with it, but not all of it, and so some of it gets reflected off. And so that's essentially what selective reflection is just some light incident upon an object being reflected off of it, but the rest of it kind of being absorbed. There's a picture here. I can snag it. Interestingly, if I have a picture of, say, just a red ball, it looks like this, right? But if I take a picture of this red ball in only red light, it then kind of sort of blends into the background. I don't know why I can't move that picture, but there's that picture. And then you can still see the ball. You can't see like this stitching so much here. That stitching is kind of white and black. You can't see it in the photo of the red ball unless you look very closely. You can kind of see it right there. But if I take the same picture of this red ball in only green light, then it looks black, right? And so the color that we see things in depends on the light that we're looking in it. And so an object's true color is the color that it appears to be in the full sun in the outside. But other than that, it may appear differently in different areas. So in fact, the light that we're in here in my face, weirdly, whenever I record these, I look like I'm, I don't know, drunk or whatever, but I get all this red looking. Maybe I look like this normally, but my face looks oddly red, but my hands don't. I don't know why, but yeah, I always look like I've been drinking when I do these recordings, and I'm not. I promise. It's tea. But the light that I have up here is I actually have two bulbs. One's an incandescent and one's an LED in my light fan up there. The incandescent bulbs tend to, focus more on the lower energy light, so they end up being more yellow and red shifted. But then the LEDs or fluorescents typically are higher energy lights, and they will make things look a little bit more blue. And so there's different lighting in the hardware aisle. You might get the cool blue, you might get the warm light. The difference is simply what end of the spectrum they're strongest in. 27.3 is selective transmission. So transmission of light is when light goes through an object. And so if I have just a regular piece of glass, it doesn't appear to be a color because all of the visible light that hits it comes and goes right through it. And so it doesn't appear to be any particular color. But there are blue glasses. There are like glass. There's blue glass. There's orange glass, red glass, whatnot. And these glass pieces of glass, if I have a piece of blue glass, it's also selectively allowing just basically blue light to transmit through it. The rest of them get absorbed into the glass itself. They get turned into heat or other energy. But then the blue transmits through, and so we see the blue, and so the glass then appears to be blue. That was a very short section, but that was it. There are other things like that. We'll talk about water in later, but objects that allow light to go through it will absorb, just like the reflected, off of my walls. They'll absorb some of the light, but in this case, instead of bouncing it off, they allow it to transmit through. And whichever wavelength, whichever color of light gets through it, is what that object then appears to be in color. 27.4 is, that's not helpful. Mixing colored lights. You're almost certainly watching this on a computer or a TV screen, and those TV screens or computer monitors have three colors. They've got these little red, green, and blue and you can actually, if you get a good enough microscope, you can look into these, or even if you get like a drop of water accidentally on your screen, you can see these red, green, and blues. And they'll just emit these lights out in certain combinations and make every possible combination of light that we can view on a computer screen. So if we take a look at what happened, Newton took I don't have a picture of it. That's a bummer. Newton took a prism and white light and spread it into the colors in the spectrum: the red, orange, yellow, green, blue, indigo, violet. And then he was actually able to take another prism and recombine it out back into white light. And so white is just a combination of all of the spectrum. White is just all spectrum added together simultaneously. But if I have just, say, a red, green, or blue, I can add red and green. Where is this picture? I have this picture. Say we have a three projectors, one that just projects red light, one that projects blue light, and one that projects green light. All three of them added together are going to make this white light in the middle, right here. Right. And then in the areas where the green and the red add together, they make yellow. And then red and blue make this, I don't know, purple, pink, whatever color. And then blue and green added together. Oh, this is magenta. Sorry, that is actually magenta. And this is cyan. But these colors, red, green, and blue, they are the primary colors. Right? And then you can add the yellow, magenta, cyan. Those are secondary colors. And then you can make more and more. There's tertiary colors, but we're not going into color theory here. We can just add light together and make all sorts of different colors. That's what your computer screen does a billion times from top left to bottom right. But the shadows of these guys are pretty interesting as well. If I can get this whole picture. We have they have actually the spotlights, and they've set it up onto a golf ball here. And so you can see the shadows here. This shadow right here has yellow light on it because the red still hits that area, as does the green, but this is the shadow of the blue light. And so that's the yellow shadow where that blue has kind of been taken away. And then this purple magenta color here is where the green has been taken away. So the red the red light hits that spot, the blue light hits that spot. So it's a pretty interesting thing to see these different colored shadows. And in a lot of like kids museums and things, they have funky little shadow walls that you can do all sorts of fun stuff with, and all sorts of colored shadows and whatnot. The light from the sun is highly concentrated in the yellow and green areas of the spectrum. So most of the light, the highest actual intensity of light is this yellowy green area right here. So it's not surprising that the human eye has become more sensitive to that wavelength, and we see that wavelength, these areas of color much more vividly, much more easily than we see, say, other colors. For instance, if it starts to get dark, we can typically see yellow and green much better than we could see red or blue in the dark, which begs the question, why are these fire engines red if they're supposed to be seen? Because once it gets dark, that fire engine to our eyes doesn't pop out like it probably should. All right, that's that for that. 27.5 is mixing colored pigments. We just said 5 seconds ago, if you add red and green together, you're going to get yellow. But if you do that with paint, I would ask you, do you think you'll get the same thing? I swear I have a picture of this. How do I not have a picture of this? All right, I don't have a picture of this. But I swear I do. All right. There's a good one. Copy this image and plop it right there. There's what happens when you mix red and green if you're in the paint world. If you're adding red light and green light, you're adding light on top of light. But this is different because this is pigments, and these pigments are reflected. They're selectively reflecting, which means the red is absorbing all of the light that's not red. The green is absorbing all of the light that's not green. And when you mix these two together, that doesn't add green to red. It takes away everything that's not green from everything that's already not red. And you get this weird, nasty, chocolatey, goopy, poop-looking garbage that is yuck. And so these are quite a bit different in adding. This is called subtractive mixing. Whereas if you're adding light to light, that's additive mixing, and it's adding the color, one color to another. This is taking away some color and then taking away different color and then mixing it and hoping for the best. It would be hard pressed to walk into the paint store and if they didn't have white, just say mix all of the colors together, it'll be white. It's not. It's going to look like, your house is going to look like a dungeon from hell, and you don't want to do that. So it's interesting to be aware of this. Artists have to know this, that kind of thing. I don't, thank goodness, because I would probably end up with walls that look like that gross stuff. I do have a picture something here. Oh, I'm in the wrong second. There we go. So with these subtractive colors, We're going to use cyan, magenta, and yellow and subtract on each other. And in fact, if I take yellow on top of magenta, the subtraction ends up being red. And yellow on top of cyan, that subtraction ends up being green, sorry. And then the subtraction of magenta onto the cyan ends up being, I don't know, whatever that is, blue. Yeah. And so we can kind of look at this as sort of an inverse operation of the additive properties of mixing light. And then in nature, there are some interesting things. This bird of paradise, for example, is, okay, there's several of them, is not blue. This little bit right here, there's no blue in there. It's just the reflection of light that gets scattered, and the bird itself actually has nothing blue in it. It's just the way that this light gets reflected off of him that then shifts and turns the light blue. Section, yeah. Okay, so I'm going to stop here on the first video. The software that I'm using limits me to 30 minutes, so I'm going to stop here and then pick up on video 2. So I'll see you there.